So how are different equalization methods related in digital communications? And here's our baseband signal representation for the intersymbol interference channel, the frequency selective channel. And for more information on this, there's a video on the channel on intersymbol interference, and you'll find the link in the details below this video. But the measurement at time k equals a summation of the current data symbol, so x0, because when I equals 0, so xk, when I equals 0, you'll have xk. So that's the current one, but also components from previous symbols, which have been smoothed out by the intersymbol interference channel and are appearing at the current time. So when I equals 1, for example, you have a component, h1, of the symbol x of k minus 1. And when I equals 2, you'll have a component of xk minus 2, and so on. And this is the intersymbol interference challenge, because at the receiver, you need to be able to try to recover the x's, which are the input data symbols. Complex numbers, don't forget they're complex numbers in the baseband representation. So I always think about what this means in a picture. I think we've got training symbols being sent, and then we've got a succession of data symbols in a packet, and then we've got a tail for the packet. And these are important, the training and the tail. So why are they important? Well, to start with the training, you first of all have to be able to work out what the channel values are if you're going to do equalization. So at the start, there are some symbols sent which the receiver knows about. It knows what those symbols are. It doesn't know what the data symbols are, but it knows what the training symbols are. And so these training symbols are used to estimate the values of H. And that's covered in other videos on the channel. But here's our challenge for equalization is that I often like to think about drawing the measured sequence. So let's draw out another sequence here, which is the measured sequence. And then we'll think about what this is. Well, at a given time, we've got, and let's pick one of these times up here, for example. So let's pick this time here. At this time here, we've got a component from, if this is time k, we've got a component, what this equation tells us is, we've got a component from xk, so this is the x sequence here that we're drawing here, and this is the y sequence that we're drawing here. So I visualize this, we've got a component from xk, because that's the element where in this summation when I equals 0, but we've also got some carryover from the value of x at the previous time, plus a component of carryover from the previous time, plus the previous one, all the way back for as long as L is. So in this case here, I'll draw an example where L equals 3. So you're getting the main component, which is the 0 component of the summation, plus you're getting 3 other components, all contributing to the measurement that is being made at time k. And of course, all the other measurements in this are also being affected by the previous values of x's. So the x's are being smoothed out and mixed up and added together in the measurement sequence. And the equalization challenge is to unravel all of that, all of this, what I think of it as a mixing. Okay, so these 4 elements here are being mixed together into that measurement, and then 3 of them are also being mixed together into the next measurement. This one's not, because in this case L equals 3, that one has contributed to the previous ones, but that's the last one it contributes to if L equals 3. But these 3 contribute to the next one in addition to this one, and so it goes as you move along. So each measurement contains information from a different set of the input symbols, and that's the important thing to be thinking about. And I think of this as like they've been collected together or mixed together, and you've got to do the unmixing. That's the equalization. So how do we do this? What are the different ways of doing this? Well, one way, and there's a video on the channel on this, is to consider this sequence in a symbol by symbol basis. So this is what the decision feedback equalizer does. And I'm going to write here symbol by symbol. And that's important for what comes later. So this is a symbol by symbol process where you are making decisions on the symbols as you go, and then you are subtracting them off from the next measurement. So in here we've got this one here is going to be that you've got your let me draw it this way. So x at time k, your estimate of x at time k is going to be taken by your measurement at time k minus the summation from I equals 1 to L of hi times the x estimates at the previous times k minus I. So these estimates that you've already made, you are going to multiply by their gains that you've learnt from the training and subtract them from the measurement at time k. And then you are going to choose, I'll just put here, pick the nearest constellation point. So I'm going to say PNCP, pick the nearest constellation point after doing this. And then you do this for this symbol k, then you will repeat the process for k plus 1, where then you've made all of the estimates from the past, subtracting them, and you're going to go on and continue to do this. This is symbol by symbol. As I said, there's a video on this in the channel. This is an ongoing process that you can continue to run there on a symbol by symbol basis. Okay, so what is another approach? So let me pick another approach here. And actually all of the others are going to be of this type. They're going to be block or packet based. So rather than symbol by symbol, they're going to be block or packet based. And what do I mean by that? Well, let me say based here. So this is all the other ones are of this type. Okay, so what you could do is you could collect all of this whole set of measurements here into a vector, and I'm going to call that y tilde. And then, of course, collecting all of the input data into a vector, x tilde, with an x tilde, so this is a vector. And then we can write all of the terms in the relationship between the elements of x and the elements of y in terms of a matrix H. Okay, and the matrix H, I think you can see, hopefully you can see by here, H, I'm just going to draw a diagram that sort of indicates what it is. So H has elements on the diagonal, because this is where xk here contributes to yk, but it also has elements on the off diagonal, on the underside here, because these are the previous, if this is this is numbered from 1, 2, 3, and so on. If you go along here and then number them down this way in that vector, then you're going to have in the H matrix, it's going to be components from the when we multiply this out here, it's going to be, let's pick this row here, for example. This one's on the diagonal, so if this is the second one down, let's say I'll pick this one as the second one down, the way I've drawn these dots here are representing elements in this matrix. I'm not saying what the numbers are, I'm just showing dots that there are non-zero elements here. So on the diagonal, this is for the second one, so y2, this was the y2 equals this component here times x2, but it's also going to be this component here times x1, because this is the amount that is carried that is smoothed out from the previous time slot. And in the case that I've drawn up here, where there were 3 components of intersymbol interference, that means there would be 3 lines down here, components here, 3 contributing elements for each measurement, and then all the rest are 0. And all of these ones over here are 0 here. So hopefully you can see this is the structure of this H matrix. And you might notice, if you're sort of carefully noticing, that there's going to be issues at the end of this matrix. And so often you put the tailing symbols here to match the last symbols from the training, so that what came smoothed out from the training into the measurements is also what you're able to measure at the end when you're measuring all the way to the end of the training in the vector y. And you include those tail bits in this vector here, and then you'll be getting components up here that are making this matrix a circulant matrix. Okay, so and these are the 3 components here that are in addition to that one there. So this matrix here has structure. You can write this as a structure when you take the entire block of measurements and consider them all together. And then we could do some linear processing. Okay, so one thing we could do is what's called a zero forcing receiver. So for the zero forcing receiver, we would be getting our estimate of x would be simply by inverting the channel matrix H, which has all the components that you've measured from the training, times the y vector. So this is a zero forcing filter to get estimates of the vector x, and then of course each of the elements of that vector are the estimates of each of the symbols. So this is a zero forcing. You can also do a minimum mean squared error once you've put this system into this matrix arrangement here, and then the minimum mean squared error filter is the H complex conjugate transposed with H dagger plus 1 on sigma squared I to the minus 1 times the y vector. So this is the minimum mean squared error. So this is linear processing. These two approaches here are linear processing to do the equalization. The DFE works very well when you're very confident of the decisions you're making, so that's high SNR, you would use the DFE. It's also simple to implement, which is one of its attractive features, but really just works in high SNR, because if you make a wrong decision, it will flow through to the others. In the case of not high SNR, you would want to be considering the entire sequence, not just symbol by symbol. And if you do it this way with the linear processing, it's low complexity, and so that's an attractive element of these linear approaches. But it may be that you're not getting good enough performance from linear processing of the measurements. So, and then the third main block, so these are, I say, block packet based linear. And then let's say the third approach here is a sequence based approach. Again, the block packet based is also we call sequence, but we put maximum likelihood. This is another approach. So sequence based maximum likelihood. In this case, let's consider what we've got if we take this whole sequence. So if we take this whole sequence, there are in fact m, if it's emery, if they're emery symbols, there's m to the power n if this is a length n sequence here, so 1, 2, 3 up to n, then there's m to the power n possible sequences. If you go through all the different combinations of the different possible symbols in each time slot, you would have m to the n possible sequences. Now it would be possible, might be, depending on how long you've got and how much processing you've got, so it might be possible to try every single one of those possible sequences and match it against the measured sequence in the likelihood function. So you could take the likelihood function, because we know that it's a Gaussian noise, it's white Gaussian noise, so we can write down the likelihood function for this, the likelihood of getting that measured vector given an input vector. And then you could try it for all the possible values of input vectors, all the m to the n possible sequences, and you could see which one gives you the most likelihood in the likelihood function. This is going to take a long time because there's a lot of possible sequences. So instead of this, you could use the Viterbi algorithm. So one thing is try them all, exhaustive search, but the other one is called the Viterbi algorithm. And there's other videos on this channel that explain the Viterbi algorithm in more detail. Again, you can find them in the details below this video. But in essence, one way to think about the Viterbi algorithm, it's similar to a sequence version of the DFE. So the DFE was symbol by symbol, but the Viterbi algorithm is almost a version of this with sequences. So this is making decisions on symbols, but the Viterbi is making decisions on sequences. And one way of thinking of it is it uses a trellis diagram and it steps through the y vector and it prunes out the possible sequences that it thinks are now no longer possible. And so it's sort of it's an iterative way of going through the measured sequence one after the other, but it's deciding on pruning out sequences now, not just considering each one on a symbol by symbol basis. It's actually a version of dynamic programming. And so this is, the Viterbi algorithm is less computational complexity than trying all the possible sequences exhaustively. And it actually, though, gives the same result. So this is why it's very attractive. It is more computationally intensive than the linear approaches, but it's if you want the performance, then you really need to be thinking about the Viterbi. The last one, I would say, in terms of these equalization methods, is to think of your modulation format. And so I'm just going to write here OFDM here because this is shorthand for doing things in the pre-coding, in fact, in the it's not actually pre-coding because it doesn't know the channel beforehand for OFDM, but it is a way of doing the modulation that helps you when it comes to equalization. So what do I mean by this? Well, the OFDM, and again, there's more videos on this on the channel, so check them out in the links below. But in OFDM, the symbols now, and I'm going to write this now as x tilde, I'm going to put a tilde on the top using two tildes here. So x tilde is our vector of symbols, but now I'm putting a tilde on the top, and these are the symbols now which are in the frequency domain. So we're still going to send symbols in the time domain, but we're going to construct those symbols differently now. So instead of, in this case, I guess it's been implied up until now that each of these symbols has come from a constellation, such as a QAM constellation. And so each time slot we've mapped from the data to a QAM constellation point, and we've sent that QAM constellation point, modulated and sent it one after the other. But another thing we could do is take those constellation points and put them in a vector, which we have now as x tilde, and I'm going to draw this as a vertical vector now, and then we take those which are then, if we do this process, then what it means is we're implicitly putting these in the frequency domain. So here we've had them in the time domain, one after another in time, but if we take that vector and then one way to effectively put it in the frequency domain, how do we do that, is to then take that vector and multiply it by the inverse of the Fourier transform matrix. So when we do this, this gives us the vector in the time domain. Okay, so if this is multiplying by the inverse Fourier transform. So don't forget, the Fourier transform takes you from the time domain to the frequency domain. So if you go from the inverse Fourier transform, it's taking you from the frequency domain to the time domain. So this vector x, which is the vector, sorry, x tilde, which is the vector of symbols we're going to send, that vector is the one we're going to send, but now we're going to generate it, instead of picking constellation points for all of its elements, now we're going to generate it by taking a vector of QAM constellation points and multiplying it by the inverse of the Fourier transform. Okay, and that then what that means is this is in the time domain, as we've been expecting and as we have to send it, but what it means is that this one then is effectively in the frequency domain. And what this means is each of our symbols now occupies its own parallel separate subchannel. And what that means is also that each of these symbols now contributes to every element of the time domain sequence. So that's, again, you have to go and look at the OFDM to really fully understand that or see a picture of that. But each of these symbols now, because it contributes to each element of this, each of our symbols lasts for the entire amount of time of that block. And so what that means is each of our symbols is now hardly affected by inter-symbol interference. This vector here is still, of course, affected by this. We now call it inter-sample interference when it's OFDM, because we think of these as a vector of samples that are being sent. The symbols are in the frequency domain. The samples still have ISI, or inter-sample interference, we call it now, but the symbols, because each symbol is in its own parallel low narrowband channel, the symbol lasts for the entire amount of time, so the amount of effect that it has on the next coming symbol is very small. So this is a way of transferring our signals into a system where we orthogonalize a set of subcarriers, which means now they don't have, each one is in its own frequency band, so each one is a narrowband frequency flat channel. Which is what we had when DFE creates a narrowband frequency flat channel by removing all of the inter-symbol interference, by making decisions and removing it. Well, this is another way of doing that. We do it by changing the way we send our symbols, and we're sending them in the frequency domain. And so that means that each one of these symbols only needs to have its constellation scaled, and then you then need to pick the nearest constellation point in the frequency domain. Again, for more information on this, check out the videos on OFDM on the channel. But essentially, this is a block approach where you're doing things at the transmitter, which means that at the receiver, you don't have the problem of intersymbol interference. So hopefully this has given you an overview of how 4 of the main equalization approaches relate to each other and their positive aspects and their implementation challenges. If you found the video useful, give it a thumbs up, helps others to find the video. Subscribe to the channel for more videos and check out the webpage in the information below where there's a full categorized list of all the videos on the channel.